In this presentation, I'm going to describe the hydrologic component of the HydroBID flood model. The outline of the presentation, we're going to analyze the characteristics of the hydrological cycle and its integration as a component of the HydroBID flood. The description of the abstraction associated with the processes of interception, infiltration, evaporation, and evapotranspiration. Description of the infiltration methods considered in the component. Terrain roughness data. Characteristic of the hydrologic component and definition of the input data. And then we are going to have an application example of the hydrologic component to on a small basin. Finally, we are going to describe the characteristics of the example of application to an urban basin, which will be analyzed in the exercise section of this component. Well, this is the schematic representation of the hydrological cycle. Sure that all of you are familiar with this hydrologic cycle where the processes of precipitation and transpiration, evapotranspiration, are the most important process because precipitation introduces the water into the system, evaporation and transpiration take out the water from the system. Well, when the precipitation occurs, first we are going to have the interception of part of this precipitation in the plant foliage, and the rest of the precipitation is going down, falling into the soil. And part of that amount of precipitation is going to infiltrate into the soil, and the excess of that infiltration is going to drain through the percolation process. This percolation process is the process that is going to recharge the aquifer that is located in this part of the soil. And where this is the water table or the top of the aquifer. Well, then this process, the infiltration process, is probably the most important process to define what is the most important component for the HydroBID flood model, that is the surface runoff component. When the precipitation rate, the intensity of the precipitation is greater than infiltration rate, and then the surface runoff process is going to start. It's the beginning of the surface runoff process. For that reason, the definition of the infiltration process is very important. And to do that, we need to know the characteristics, the most important characteristics of this zone, that is the unsaturated zone of the soil. In the case of the hydrologic component, the philosophy that is behind this component is the following. We consider this basin when we have this upper basin, when this rainfall event is occurring, and we have the different components of the hydrologic cycle. And we are interested in analyzing the inundation problem or flooding problem in this urban area. And then in the past, to do this, we use two kind of modeling. The first one was in the upper basin, we apply a hydrologic model. The idea of applying this hydrologic model in the upper basin was to obtain the hydrograph, that is the variation of the flow with respect to time, the hydrograph in the upper basin that is going to represent the response of the basin to the occurrence of a specific storm. Let's say that we're analyzing the centennial storm, that is a hundred years return period storm, and that hydrograph is going to be the response to the occurrence of that storm. Having this hydrograph entering into the lower basin, and then we apply a hydraulic model. That was the general idea that we did in the past. And with this hydraulic modeling, and then we do the routing of this hydrograph, and doing the routing of the hydrograph, and then we determine the basically the depth of the water and also the magnitude of the velocity vector. In this case, we have velocity, the magnitude of the velocity in feet per second or meters per second, but also we have the direction of the vector velocity. With that information, then we can, it was possible to analyze the inundation problem in that urban area. Well, in the case of the hydrologic component of the HydroBID flood, the philosophy is to integrate both methodologies, because both methodologies are interconnected. From the physical point of view, both the hydrology and the hydraulic are occurring at the same time. In the sense that, first of all, the rainfall not only occurs in the upper basin, also can occur over the urban area that we're analyzing, where we're analyzing the flooding problem. Therefore, in this case, we can consider that rainfall over the whole basin. And in addition to that, the hydrologic, analyzing the different components of the hydrologic cycle, we are going to define that runoff, the surface runoff component. And that surface runoff component, a HydroBID flood model is going to use that to route this surface runoff component through the basin and also through the drainage network of the basin, considering and then the problem related with the flooding in the urban area, where using this kind of modeling, we can analyze this in detail, defining the depth of the water and also the velocity, the vector velocity. And then, as a summary, the hydrologic component is an integrated hydrologic and hydraulic model that consider runoff, losses, flood routing, everything, but as a whole model, as a unique model. To understand then, to define this surface runoff component, that's our goal, that we want to determine that, first we have to analyze this hydrological abstraction. These hydrological abstraction are losses that we have the precipitation process, but part of that precipitation is going to be intercepted in the foliage of the plant, as I said before, in the interception process. But also we are going to have here a surface storage. Part of this surface storage can be evaporated, and then the effect of evaporation over the surface water, but also the evapotranspiration. The evapotranspiration, that is the combination of the evaporation process and the transpiration of the vegetation covers. But the most important process in this abstraction analysis is the infiltration. Because this infiltration is the process that is going to determine, when we compare the intensity of the rainfall with the infiltration rate, then we are going to define the surface runoff component. Okay, in the case of intersection, then the first abstraction, hydrological abstraction, the first type of hydrological abstraction. This intersection is an important topic in storm modeling, but in the low-intensity storm are substantially abstracted by intersection. But in the case that we are interested on, that is the occurrence of extreme storm like a centennial storm or the 50 years return period storm, those are high intensity storm. In these cases, the interception is generally a very small fraction of the total rainfall, and then it's not very important. Then the important abstraction is that is produced by the infiltration process. The infiltration is considered the main abstraction mechanism in the storm event models. That's the reason why the infiltration is the most important process in defining the amount of surface runoff. Infiltration is going to be a function of the soil physical characteristic that we describe as a soil physical characteristic, knowing the soil texture, and also is a function of the vegetation cover and the land uses and the topography. What happens is that the soil texture, vegetation cover, and also the topography are changing in the space. Therefore, analyze this infiltration process in the space is a very complex. In the case of surface storage, in a small and mountainous basin, surface storage is usually negligible. But in the case of urban drainage and lowland, it could be important. And then the process of evaporation and evapotranspiration. We can measure the evaporation in this type of a Class A evaporation pan. Those are the dimension of this Class A evaporation pan. And this is a picture of one of these evaporation pan. We can measure here the evaporation and relate that evaporation with the evapotranspiration. That's a possibility, but also the evapotranspiration can be estimated using the potential value, the potential evapotranspiration using the methodology recommended by the Food and Agriculture Organization. That is the methodology developed by Raymond Montier. But because when we're analyzing evapotranspiration, we are interested on actual evapotranspiration. That actual evapotranspiration is going to be a function of the potential evapotranspiration that will be a function of the time of climate that we have in the basin and the soil water content. But and then we can apply this methodology. But this methodology is very important when we are analyzing continuous modeling process. We are modeling the continuous process like water balance in a basin that using a period of days or several months or several years. But when we are considering an storm event, that the duration of the storm is going to be like 4 hours or 6 hours, maximum 24 hours, the evaporation is not that important as it is in the continuous modeling. Because in this case, when we compare the amount of evaporation in 6 hours, evapotranspiration in 6 hours with the total rainfall, that amount of evapotranspiration is going to be small compared with the total rainfall of the storm. This extreme storm that we are using to analyze these problems related with flooding and inundation. Well, then the infiltration is going to be the process most important in this definition of the surface runoff. The infiltration rate it is expressed in inches per hour or centimeters per hour, and it is the rate at which water enters into the soil, the surface of the ground surface. The surface runoff process begins when the rate of water supply, that is the intensity of the rainfall, is greater than the potential infiltration rate. Okay, the cumulative infiltration that we are going to, the notation that we are going to use is this capital F as a function of time. Capital F of function of time is going to be the integral between 0 and t of this lowercase f as a function of tau, differential tau, when tau is a dummy variable of integration. But this is the infiltration rate, because the infiltration rate, by definition, is the derivative of the cumulative infiltration with respect to time. Well, the infiltration rate, we can measure the infiltration rate in the field using these infiltrometers. These infiltrometers, like this one, we can introduce that infiltrometer into the soil, fill the infiltrometer with water, and then measure the dynamic of the depth of the water depth. And then we are measuring the decreasing with time of that water depth. And that information is going to give us the cumulative infiltration. And having the cumulative infiltration and as a function of time, we can obtain the infiltration rate as a function of time. When we have this information that we can measure in the field, we can use that information to calibrate the parameters of the equation that we are going to use to analyze the infiltration process from the theoretical point of view. Okay, to understand this process, we have to analyze the characteristic of this type of flow, that is the flow in the soil unsaturated zone. The soil profile where this process takes place is known as the porous medium. The flow in the unsaturated zone is that which occurs when the porous medium still has part of its porosity occupied by air. This zone is located between the ground surface and the water table or phreatic level or the top of the aquifer. The excess water that leaves this area flows downwards, producing the process known as percolation, I said before. This percolation is going to recharge the aquifer or the saturated area. Below the water table, the area becomes saturated and the pressure is higher than the atmospheric pressure. Now let's consider the flow in the unsaturated zone. To do that, we are going to see this figure, and this figure that has been taken from this reference, Benteschow et al. In 1994, where we can see this surface control, the soil particles here, and the water around the soil particles that are retained in the soil for the adhesive and cohesive forces that makes the what I call the soil water content is because of this soil that is covering around the soil particles. And we call this unsaturated zone because the rest of the porosity is occupied by air. As you see, this is air, this is water, and these are the mineral particles of the soil. Well, let's make some definition. Then, first of all, let's consider the porosity. This porosity is represented by this Greek letter eta, and it's going to be the relation between the volume of the voids divided by the total volume of the soil. And that's the porosity. And the porosity, the range of value of the porosity is between 0.25 and 0.75. Another definition is the hydraulic conductivity. The hydraulic conductivity represents the ability of the porous medium to allow the water flow. According to the Darcy equation, this equation that we have here, this Q is the flow per unit area in an aquifer. That is going to be equal to the hydraulic conductivity multiplied by the hydraulic gradient. That is like a slope of the water table. And that's the definition. How can we use this hydraulic conductivity to define the flow per unit area in an aquifer? Another definition is the soil moisture content. We are going to use this Greek letter theta. Theta is equal to the volume of water divided by the total volume of the soil. And the range of the value of this theta is going to be between 0, when theta equals 0, we have a dry soil, and when theta equal to the porosity, equal to eta, it's going to be saturated soil. That's the condition of saturated soil. Okay, and to define these parameters, we use this textural classification of the soil. This textural classification of the soil, to do that, we use this soil textural triangle that has been defined by the Natural Resources Conservation Service of the U.S. Department of Agriculture. That is this triangle. Okay, and then to characterize the soil, what we do is we open a pit, soil pit, and in this soil pit we can describe each one of these soil horizons. We can see those horizons in this soil profile, where we can have a small horizon at the beginning, that is an organic horizon, and then we have the horizon A, that is the surface horizon, horizon B, where we have the root of the plant here, is the subsoil horizon, and the horizon Z, that is the substratum horizon. Well, to characterize the soil, what we do is then we take a sample of the horizon, the sample of the soil, we send the sample to the lab, to the laboratory, and in the lab they are going to determine the percentage of clay or the percentage of silt and the percentage of silt and the percentage of sand that this sample has. And then suppose that the result is that the sample has 30% of clay, 30% of silt, and 40% of sand. And in this case, the textural class is clay loam. And in this way, and then we can define the different textural classes that we can have: clay or sandy clay loam or silt loam or silt or sand or clay, and so on. Because what happens is that we are going to relate the texture of the soil with the value of the parameters that we are going to use in the equation that define the infiltration process. The first equation is the Horton equation, maybe the most popular equation. Um, Through experimental observation, Horton found that after the infiltration rate begins with the value of F0, we can see this graph here where we have time in the abscissa and infiltration rate in the ordinate, and then we have a value of S0, that is the initial infiltration rate. And when the experimental observation of this infiltration rate was this, that the and occurs an exponential decay of the infiltration rate until to reach an asymptotic value, and this asymptotic value is what we call FC, that is the basic infiltration rate. And then using those type of information, that is the initial infiltration rate and the basic infiltration rate, and also this kappa, that is the decay constant, and this is the exponential decay, and then we can, using those parameters, define what is the Horton equation that define the infiltration rate as a function of time. The time is here, multiply the exponential to the minus kappa multiplied by time. Well, this is, and then the Horton equation, and that's the how this infiltration rate is has this decay, exponential decay, until reach this asymptotic value. Okay, and the relationship between the infiltration rate and the cumulative infiltration is this one. Okay, time here, and then or cumulative infiltration or infiltration rate. And I said before, the cumulative infiltration can be measured in the field using infiltrometers. The those infiltrometers give us that information can be used to calibrate those parameters of this equation, of any infiltration equation. In this case, the parameters are going to be F0, FC, and kappa. Okay, another methodology is the proposed by Green and Amp. Green Amp, that is called like Green Amp equation in Green Amp methodology. This methodology represents a better approximation to the physical theory that determines the infiltration process. To understand that, let's look this cylinder that we have in the lower right-hand side of the slide. We have this cylinder full of soil, and at the top of the soil, we have a supply of water, and then this depth L, we define the depth of the wet soil, and this is going to be the wet in front that is moving downwards over the dry soil. And then we have the wet soil, the wet in front, and the dry soil. And this is the ground surface, Okay, we can represent this using this figure. In this figure, this is L, and then this is the supply of water, and we have here this water. In this case, this X value is going to be theta, that is the soil water content. When the theta is equal to porosity, we are going to have saturated soil. And then that's the reason this one is the wetted zone with the conductivity equal to the hydraulic conductivity. And this is going to be the wet in front. And theta I is going to be the amount of water content retained in the soil before the storm begins, and then before the infiltration process begins. Yeah, really, the infiltration process begins. And then the difference between the total porosity minus this theta I, we are going to give us this parameter that is delta theta, that we are going to use this parameter as in the equation or Green-Am equation. Also, we have the theta E. The theta E is the effective porosity. This effective porosity is related with the textural class of the soil, and using that value, we can make the estimation of this delta theta. Okay, well, and then to apply the equation of the Green-Am method, we need that we need the saturation condition in the top of the at the ground level of the soil, and the top of the soil. But and then when we have a storm occurring over that soil, at the beginning that soil is dry, and then the soil is going to reach that saturated condition at the time Tp. We are going to call that time Tp, where time is equal to Tp. The soil at the ground surface is going to be saturated. And that occurs when the infiltration rate is going to be equal to rainfall intensity. Because when the rainfall intensity is greater, equal or greater, in this case greater than infiltration rate, the surface runoff process begins. And then we have to define this Tp. To define this Tp, and then what we do is we use this equation, that is the equation defined by the Green-Am methodology to obtain the infiltration rate, and then we are going to make this F equal to the rainfall intensity. And then the rainfall intensity is going to be equal to the equation, and this cumulative infiltration is going to be the product of the rainfall intensity times Tp, where Tp, remember, is the time at which the surface runoff process begins. And then using this equation, we can solve this equation for Tp, and we are going to obtain an equation like this one, where Tp is going to be a function of the soil physics characteristic and the intensity of the rainfall. Well, C is the wetting from soil suction head. That is another parameter that is going to be a function of the textural class that characterize the soil physics characteristics. Well, and then when T is less than Tp, we are not having saturated soil, but when T equals Tp, we are going to have saturated soil at the ground surface, and when T greater than Tp, we have this wetting from moving downwards. And then when we have this saturated soil at the top of at the ground level, we can apply the general equation of Green-Am methodology. The general equation says that the cumulative infiltration at time T plus delta T is going to be a function of the cumulative infiltration in the previous time step and the soil physics characteristic, and that can be estimated, those parameters, using tables like this one, this information that is contained in this table, where we have the soil texture here. And for the different soil texture, we have the value of the porosity, of the effective porosity, of the wetting front suction, soil suction head, and the hydraulic conductivity, where this is the mean value of the parameter, and those are the one standard deviation around that mean value. And then this is the range of the value that this parameter can have for this class of texture, textural class. Well, and then when we compute the value of cumulative infiltration, the variation of the cumulative infiltration respect to time, we can plug that value here and obtain the corresponding infiltration rate for at that time. Well, that's the application of the Greenham method. Another methodology that probably you are very familiar with it is the curve number methodology developed by the Soil Conservation Service. In this methodology, the hypothesis or the methodology is this relationship that we have here, where this S is a very important parameter because it is the potential maximum retention. And then this value is very important, and also this continuity equation, we can understand this continuity equation analyzing this figure, where the axis is time and the ordinate is going to be rate of precipitation rate and infiltration rate. And then this is the yetograph, the original yetograph of a given storm expressed as a rainfall intensity, and this is the infiltration rate. And then using this information, we estimate this IA, that is initial abstraction, then Fi, that is going to be the continuing abstraction, and this PE, this PE is going to be the rainfall excess, and this rainfall excess is the surface runoff. That's what is important to define to run the HydroBID flood model. That's what we are interested in defining. And then, well, this total precipitation is going to be equal to PE plus IA plus FA. And using this equation and this previous relationship, we can then obtain the general equation of the curve number methodology, where knowing this potential maximum retention and the total precipitation of the storm, we can obtain the total surface runoff. Okay, let's see this figure on this table, because using this table, we can obtain the runoff curve number. That is going to be a function of the land use. Those are different type of land uses, and here we have different type of soil that we classify this soil using these hydrologic soil groups. There is the soil type A, B, C, D. A is more like sandy soil. B is loam, sandy loam, clay loam, and D is like a clay soil. And then using the type of soil and the land use, we can estimate the value of the curve number. Let's suppose that we have this curve number equal to 60, and then what we do is, in this equation, we introduce here the value of 60. We solve this equation for the value of S, the potential retention, maximum retention, and introduce this S here, and using the precipitation of the storm, we then can estimate the excess, the precipitation excess, or the cumulative direct runoff, or what we are calling a surface runoff. And then, let's analyze this relationship between cumulative rainfall precipitation in inches and cumulative direct runoff or effective precipitation in inches. If we have this cumulative rainfall precipitation of 5 inches, and we are using this current number of 60, then the direct runoff is going to be like 1.3 inches. And the ratio between 1.3 divided by 5 define what is called the rainfall runoff coefficient. In this case, the runoff coefficient is going to be 26%, expressed in percentage values. And if we, instead of having a storm of 5 inches, have a storm that is where the precipitation reached the value of 10 inches, then we go to this curve of 60 with the core number of 60, and the direct runoff or effective precipitation is going to be 5 inches. The ratio between 5 divided by 10 define then the runoff coefficient, that in this case is going to be 50%. And then when we increase the precipitation, the runoff coefficient also increases. That means that the runoff coefficient is not a constant value. The runoff coefficient is going to change with the amount of precipitation. Because there are some methodologies to define this direct runoff, use a constant value of the runoff coefficient. But in this case, this kind of methodology include this variation of the runoff coefficient with a precipitation amount. Okay, well, we want to obtain as a final result is this one. This one is the effective yetograph. The effective yetograph, in this case, is expressed as rainfall excess depth in centimeters, and we obtain this effective yetograph superimposing to the total rainfall yetograph, but this is expressed as intensity in centimeters per hours, with the rainfall, the infiltration rate. And then when we're comparing the infiltration rate with the rainfall total yetograph, we're going to have something like this. That at the beginning, we're going to have the initial abstraction, and after this point, that is time equal to 60 minutes, we're going to have the continuing abstraction, and this difference between the continuing abstraction and the yetograph is going to define the excess of rainfall rate. And this is going to be the surface runoff. That if you accumulate these values, when you accumulate this value, we're going to have the initial abstraction, then the continuing abstraction, and the difference between the cumulative total precipitation, and this continuing abstraction plus the initial abstraction, we are going to define the cumulative excess of rainfall. And then using this cumulative excess of rainfall, we can obtain the incremental excess of rainfall, and the incremental is going to be this figure that we have here. And that's the information that we have to give to the HydroBID flood model to start the routing procedure, because we are going to route that rainfall excess or surface runoff through the basin and through the rainfall drainage network of the basin. Then to define the yetograph in the different section of the basin associated with what is going to be as a response of the basin of the occurrence of this type of total yetograph, and taking into consideration the characteristics of the soil and also of the vegetation cover and land uses. Okay, another parameter that is important is the roughness coefficient of the Manning equation that we call N value. The N value also is going to be a function of the type of land uses or vegetation cover. Well, in general, the characteristic of the hydrologic component is a distributed model because, for example, in this case, is the different colors represent the different land uses and vegetation covers that are going to have different values of Manning or the roughness coefficient of the Manning equation. And then taking into consideration the variability, the spatial variability of this parameter, the roughness coefficient of the Manning equation. But also is take into consideration the spatial variability of the rainfall, on also the evaporation, and also the infiltration parameters. The infiltration parameters are going to change in the space, and the parameters are going to be defined depending upon the kind of methodology are we using to estimate the infiltration process, or the Horton equation, or Green equation, or the Soil Conservation Service CN curve number equation. And then in the case of the rainfall and evaporation, we define different regions, different polygons, and associated with each polygon, we have to define a time series of that represent in the case of rainfall, the rainfall yetograph, total yetograph associated with each region. We have 3 regions. We are going to have 3 yetographs. Okay, but in general, the methodology allows any kind of rainfall input. Could be the rainfall that we can obtain through radar or rain gauges, etc. In the case of infiltration, also we have to define these polygons. Different polygons, we are going to have different parameters for the infiltration equation that we select to represent the infiltration process. Then, as a summary, the required data to run the hydrologic component is the first rainfall and evaporation, that can be the precipitation time series for each rain gauge, and then defining the polygons of influence of each rain gauge, or grid files of ASCII, expressing ASCII format that can be obtained through radar, for example. In the case of infiltration, also polygons that define the different regions of the infiltration parameters, and also define the kind of methodology that we are going to use to represent the infiltration process in each polygon. If Horton, those are the parameters. If it is Greenham, those are the parameters. And if soil conservation service methodology, those are the parameters. And also, we have to specify the Manning N, or the roughness parameter of the Manning equation. Also, we can do it through polygons, that those polygons can be associated with the land uses, for example. Okay, let's analyze this application. We are considering this watershed, a very small watershed. It's 67.74 hectares that is located in the uh, is located on the southern slope of the Cordillera de la Costa, that is located north to the city of Caracas. This is the city of Caracas. The characteristic of this basin, from the land use point of view, we have this different type of vegetation, like forest or grass or shrub here, and this is the kind of forest that we have in that watershed. And this is the riverbed cross section of the watershed. To represent the watershed, we use this digital elevation model with the resolution is 1 meter by 1 meter resolution. This is the yetograph that is going to be the centennial yetograph. The return period of the yetograph is 100 years. We are considering 4 hours storm, and a storm of 4 hours duration. And that's going to be the meteorological input data to the system, to the HydroBID flood model. Okay, and then this is we can the mesh do the mesh the meshing process in the basin, where we have different sizes of the triangles component of the mesh. In this case, we are considering more than 46,000 elements. The size of the mesh indicates when we define the drainage network, the size is going to be smaller than we have in the floodplain. Also, we have to define the boundary condition of the outlet of the basin. And then using all the information, we can export that information to the HydroBID flood model. And using this window, we define the time of simulation. In this case, we are going to simulate during 4 hours. And in the component, we have to select the precipitation and evaporation, but also infiltration. And if we click here on the said precipitation and evaporation and the infiltration, we can verify the information that we have in each one of those components. In the case of precipitation and evaporation, here is the yetograph of the precipitation, and here the data of the evaporation, in this case for different hours. And in the case of the infiltration, those are the different polygons, and associated with each one of them, we select the soil conservation service core number methodology, and then we have to define the core number and also the initial abstraction, the constant that define the initial abstraction. Okay, and then we run the model. Click in this button here, and the result is going to be this one. This is the hydrograph at the outlet of the watershed. In this case, the peak of the hydrograph is close to 14 cubic meters per second. And we also, here when we have the outlet of the watershed, we can define this cross-section. And defining this cross-section, we can and then obtain the graph of the hydrograph in this cross-section, the outlet of the watershed. But also we have a table. We can obtain this table, and we can copy that table in the clipboard and then export that table to, for example, an Excel a book, to do any another type of analysis. Well, now we run the model again, increasing the number of elements of the mesh. In this case, now we are considering 182,000 elements. We're running this alternative or this option with this detail. We have more detail because we have much more elements. The peak of the hydrograph is going to be like 19 cubic meters per second. Remember that when we run the program with 46,000 elements, the peak of the hydrograph was like 14 cubic meters per second. And what we do in these cases is that we start increasing the number of elements and running the program up to the point when, if we increase this number of elements, instead of 182, we have 250,000 elements, the peak of the hydrograph is going to be the same, 19 cubic meters per second. At that moment, well, that means that that's the solution, that's the result associated with this example. Okay, now let's analyze the characteristic of the urban watershed to be used in the exercise on the application of the HydroBID flood to a pilot watershed. That you are going to use this information to run to do the exercise associated with this component. Okay, this is a watershed that the area is 191 hectares, almost 2 square kilometers, which has a high urban occupation, 36% between industrial and residential areas, 30% informal housing. Okay, this is the area with informal housing, 13% with intervened green areas, that is this color right here, and 21% of forest green areas, natural forest, and this is the area of the industrial zone, and okay, and this is the formal residential area. Formal housing here, informal housing in this area, industrial, forest. Okay, we can see the study area and using the Google Earth, and if we define using this digital elevation model of 1 meter resolution, we can obtain the domain outline. This is the domain outline. This is the industrial area. And this domain outline, we can now have this domain outline with the background picture of the Google Earth, and you can see the complexity of the land uses that we have in this watershed. Informal housing, residential areas, industrial areas, forests, and so on. Well, with this, we finish this presentation. Thank you for the attention.